this coal fly ash and things like that, but it's related to all composites and all materials which you can make. Then coal fly ash composites will be also a part of that. Now, at the bottom it says this copyright for this work is owned by the School of Material Science and Engineering, is mainly because I used to teach them, and there it's a standard practice for their school to say that this is copyright of School of Material Science and Engineering. So, but at the same time, there's a standard practice, but you have seen most of the work has been taken from different, like American societies and different other things. So they're copied and they are given. So I don't mind if you take the copies of this, okay? But then if you take then go back to some of the earlier publications and things like that. But this we have summarized, it's a very broad area, and we have summarized like that. And I summarized it, put it like that so that it does not take too much time. About half an hour, 45 minutes, but that gives enough information. Okay, looks like everyone is coming back. Failure modes can be instantaneous, and that means brittle failures. Instantaneous means if something all of a sudden happens. I almost did yesterday. Yesterday, I was trying to take a shortcut going back, and then my feet entered into a hole all of a sudden. And I realized I was going to have an instantaneous failure of my foot bone. But before anything happened, picked up. That means it happens within a fraction of a second, or it can happen in a microsecond. All right? And that must be avoided. Because if you have instantaneous failure, that means it will generate a crack there. And if it generates a crack there, then you have to make sure that the crack does not extend. So instantaneous failure or instantaneous crack generation can happen. Now, when you say failure can mean the failure of the structure. It can be local failure, all right? It can short-term failure. So anything can be part of that. So don't get upset if it's a failure, all right? Sometimes if people fall down and you have a twisted finger and things like that, that's an instantaneous thing. But put it under hot water and it can get back. You get the pain relieved. So instantaneous failure means something, deformation has happened, and the stress concentration, stress transfer is not working. That is what it means. Progressive means once you have that defect, unless you take care of the defect, and if we leave it under stress and things like that, the defect will grow. So it's better always, if something happens, investigate and make sure you put something, it's like a medication to the defect so that it does not grow. It stops there. Or otherwise, if it is a sharp crack, put something there so that you, like often aircrafts have this same defect. And here I'll take it a pride to mention that Australian Defence Science and Technology Aeronautical Research Laboratory, they had developed a technique whereby aircraft which has carbon fiber composites, if they crack, earlier the Americans used to throw them away. But then Dr. Alan Baker and his group, what they try to do, wherever there is a crack, they try to put back epoxy resin and cure it there. And that means that crack defect was filled and the crack was removed. And then that became a big American technique also. I remember once I had gone to a conference, ICC, International Conference on Composite Engineering, and then there was one group given a table and they were talking about how to rectify the defects of composites like in the aircraft. And then I was standing there, I realized that it was our Australian technology, Dr. Alan Baker's, which was taken up by them. But I had a big satisfaction in my mind. And then politely I said, thank you, but I come from that laboratory where the senior principal scientist, Dr. Alan Baker, had developed the technique. So that was a nice friendliness, friendship. So we are happy that Australian Defence developed the technique, and we are also further happier that the American aerospace industry and they adopted the technique, and they don't know always who developed the technique, but that's not important. You have the technique and you develop it. But because I was a part of that institution and I knew Dr. Baker very much, and for whatever reason, Dr. Baker liked me very much. So he was, I loved him, I respected him. I don't know why he loved me also. He said, Bando, I like you very much. I said, thanks, Dr. Baker. Okay, he's a great man. He's an aeronautical engineer and he worked so much in the fiber reinforced plastics. If you ever, his name will be, I mean, he has now taken retirement, but his name will be the Alan Baker, A-L-A-N-B-A-K-E-R, Dr. Alan Baker, and he was a part of DSTO, Defense Science and Technology Organization. Now, failure is instantaneous, then it's progressive. That means it does not happen instantaneously. It takes time. That means different types of loading and things are there. And there will be crack tip opening and crack propagation. Okay. So, instantaneous is ductile overload. Like I said, when I through mistake my foot went in a hole in a concrete hole. One of my fingers, left finger, it was squeezed and deformed. So that's a ductile failure. But then I knew how to do it, so I didn't tell my wife that I had this. Then she said, why did you go through that side? Why couldn't you come through this? Because I didn't want to hurt her. So in the evening I have a bucket full of water. I put my feet there and let it be there for some time. And then gradually that stress flew away from the tip of the feet, okay? Because I did fracture mechanics, so this simple fracture mechanics experiments are useful for my, so. Brittle overload means if the material is something which cannot undergo plastic deformation, then all of a sudden if there is brittle overload, it will generate a crack. But even if it generates a crack, it does not mean it's the end of the day. Once you have the crack, and it will have a crack, never get upset on anything. God has given us the brain, so whatever the nature does, whatever the mechanics does, you always have the better ability. Never ever get upset. Look for solutions, okay? I hope I'm not saying anything wrong to you. Okay. Oh, thank you. See, yes, God has sent me a bag. Because I wanted to have a bag because my wife will just sometimes ask me, you have come here, but there is no proof that you have come here. How do you know? How do I know that you are going every day for lectures and things like that? Okay, so I have to show some proof to her. And also, मेरा एक कार्ड भी दे देना. लोगों का नाम लगे, मेरा कोई नाम नहीं है, मेरी बीबी पूछेगी, आपका नेम का कार्ड कहाँ पे है? Okay? All right, thank you. I have to have some proof. Progressive is fatigue. Okay. Fatigue is up and down, stress going up and down. Likewise, so when you walk a long time, 1 hour, 2 hours, sometimes you feel a lot of pain. So again, it will go down. So fatigue is cyclic loading. Corrosion is a bit bad. You know corrosion. You can have corrosion under stress. You can have chemical corrosion. You have physical-chemical corrosion. Then what is creep? Creep is when you have a load, sustained load over a period of time, the deformation goes up like that, okay? So initially, this is time, this is deformation. So initially it may go up like that, and something like that. That is created very, after it may take a long time to progress, and then as the time goes up, the deformation will go up. This is the creep is going up. After some time it can do like that, or in some cases it might even go and fail. So this is failure. So creep, this is deformation. Creep is under constant stress. So if there is a constant load on the material and there is a void, that void can grow over some time. And that's why all planes and structures, they have regular inspection of their composites and things like that. So they come and go, but sometimes every maybe 3 or 6 months, so the plane is put it in a checking chamber. And this is with all this non-destructive testing, things are so much easy. Okay? Non-destructive testings are very useful. And what is wear? Wear is when two things just rub against each other. All right? So that is kind of thing is generated scratches and things like that. So these are failure modes. Methods of examination. Fracture surface, we have seen some. So the cross section through the fracture. Visual and low power light microscopy. Light microscopy is available almost in all departments, particularly in materials science and materials engineering, and also all engineering. And you get typically 1 to 50% magnification. If you go more than 1 to 50% magnification, when you talk about magnification, this is linear magnification. So what is the aerial magnification? 1 to, what is 50 square? 2,500. So please keep that in mind. And whenever you show a picture, you are showing a picture or anything, always put a scale. Even if it is low thing, just put a normal scale bar, just ruler or something like that. Okay, but otherwise, you will find in all electron microscope pictures there is a scale there. But also remember that's a linear magnification. If you're going to aerial magnification, so you have to multiply it by the same thing so that you give what the area is. Electron microscopy is another thing which is very useful. And today I added EDS and SIMS. So now please also include EDS and SIMS there, because that's what normally people do not do that. But that's why it combined everything. If you put EDS and SIMS, cross section through the fracture. If you have electron microscopy, then 20 to 10,000 magnification, again linear magnification. So that means if you are doing at 20 linear magnification, is aerial 400. If you are doing 10,000, if you are doing linear, that means it's about square wise is 10,000, 10 to the power 4 times 10 to the power 4 is 10 to the power 8, which is about 100 million, is it? Yeah. So it's not always possible to go for all that, but electron microscopes are capable. But sometimes the highest magnification I had shown you was about 1 micron or 2 micron in the linear scale. So from there you can work it out. The cross section through fracture. What it means, if we have a fracture, okay, if this is a sample, let me take a white sample. Let me take a yellow sample. If this is a fracture and I bend it in failure, so that is the cross section, that is the area which I'm, so if you want to see that, you cut it with something and do not rub anything, do not put any grinding on anything, and then cut it and put that on fix that on a aluminum plate, and then if you're doing ACM, put that thing in a structure, it will coat the top part with gold, and then you put it in the electron microscope. Because the electron microscope can use the gold, and the gold will help the conduction of the electrons. But one thing, if you are using with polymers, things like that, and if you want to see the difference between the polymers, you can also use without coating gold. So we had, when we used to do defense, I did not have any teaching to do, so I had all the time left for research. And in the physics department, they had electron microscopy, and the in charge was Mrs. Veronica Silva. She was originally from England, and she was very nice. And I used to go and do lots of work there, and she gave me the access to the electron microscopy. And what happened, if you are using polymer, and within polymer, if you have a fiber, using polymer as a matrix, if you go to very high kilovolts, the polymer can't be burned by the electrons. Okay, so sometimes you will get information or faults which is not actually a part of the structure, but part of the electron microscopy, electron. So that is what you need to do. So it is better to use, instead of 20 kilovolt, it is better to use much less voltage. But if you use much less voltage, it will also have certain problems. So sometimes what I used to use some fillers which are used in transmission electron microscope, which has electronic conductivity, and I used to put them in the structure. So that itself would give very small electronic conduction. So these are the ways by which you can actually solve the problems, okay? But if you are working with plastics, for example, majority of the paper was fly ash and polymers, it is difficult not for the plastic not to burn, whether it's thermoset or whether thermoplastics, if you are going to 20. So try to use lesser voltage there, okay? And develop your own techniques. And if you have any difficulty, you can send me an email and I can think of something or I can suggest, all right? So the cross section through fracture, that means you break the top part and do not do any damage to the top, break the bottom part and put it up there, so that electron microscope will give you a good cross section. Ductile and brittle failures characterized in terms of amount of macroscopic plastic deformation that precedes fracture. So this is a beautiful way of saying what is ductile and brittle failure. If you have very small macroscopic plastic deformation that precedes fracture, then that's a brittle fracture. If you have good amount of macroscopic plastic deformation, that's a ductile fracture. So why? That means if you have good amount of microscopic plastic deformation, that means whatever energy you have given there, whether it is a train, bus, tram, or your own foot, or that plastic deformation is taking up all the energy. All right? And then, so the crack is not getting much of the energy. You may have a defect, but the defect is not getting much of the energy. The crack cannot proceed. But if the plastic deformation is amount of plastic deformation is very low that precedes the fracture, then it's almost a brittle fracture. Or sometimes it's called a pseudoplastic fracture, okay. So this is a element of ductile fracture here, ductile A and B brittle fracture. Okay. So this is a ductile fracture if you look it from the top, and if you look it from the side. Here you will see this is a specimen, metal specimen done in Instron. So this is the original diameter, but then it shrinks. The diameter goes down, and this is how this is a ductile fracture. But if you are doing a fracture of a ceramic material, there is no going down of the diameter. So this is almost a brittle fracture, and here you can see there is no reduction in the diameter of the specimen. So these are brittle fractures, and these are ductile fractures, and these are brittle fractures. Here you can see this lot of plastic deformation is happening, and plastic deformation, if you go back to this stress strain diagram, plastic deformation goes up the yield point and it keeps on taking things. So that's what's happening. And in the brittle fracture, as soon as you go after the yield point, it comes down. So that, and how do you measure the energy? It would multiply the x-axis and the y-axis, that gives you the energy. So in the case of brittle fracture, you get that, but you are losing all that other part of the energy, okay? So that is what is happening. Ductile and brittle failures in terms of amount of macroscopic plastic deformation. First we said microscopic plastic deformation. Now you can see macroscopic. Ductile is appreciable gross plastic deformation, tearing of the material, expenditure of considerable energy, whereas brittle is no gross plastic deformation, rapid crack propagation, and low expenditure of energy. So of all the things, if you ask me to say, out of 3 items in each, under this status, which one you should remember, we should remember, is expenditure of considerable energy and low expenditure of energy. So that is the most thing, because if all the energy that is there, and if the material takes it up, then the crack says, oh my God, no one is giving me any energy. And the plastic deformation is laughing. Yes, you stay there as you are, you stay for 100 years, you will not, no one will give you any energy. All right? But brittle it says, I don't need any energy and I'll grow. So this is depending on macroscopic aspects of deformation. Ductile overload failures at low macroscopic magnification. It can be matte, fiber fracture surface, and either flat or oriented at 90 degrees to maximum tensile strength, or shear, oriented at 45 to maximum tensile strength. So this is how it looks like. This is not a human body, okay? This is the sample. So this is the specimen diameter. Originally it's a cylindrical one, and as you're loading, it becomes thin and thin. Remember, I showed you one picture there where it was, and eventually it cracks. So that is the tensile stress prior to fracture. So this is the flat plate tensile fracture. There's a lot of deformation there. Features are produced by a triaxial stress system. What is the triaxial? You have stress along X is the length, Y is across the thickness, and what is the Z? Z is from inside to outside or outside to inside. So there is X. Normally we don't think of X, Y, Z, but there is a Z. Z is across the thickness. Okay? So please keep that in mind. So produce a triaxial system. And under the triaxial system, in the previous figure, under the triaxial system, there's a flat thing here is going. So that's how the fracture surface is. Fracture is preceded by necking. That's how it, again, the same thing, became flat. And plane of fracture is at 90 degrees to direction of largest tensile stress. The plane of fracture, if the tensile stress is going on like that, the plane of fracture is about 90 degrees to that. That means this crack is propagating in this direction. So flat face tensile fractures. Shear face tensile fracture, produced under plane stress condition, thin or shear or near surface, okay. Plane of fracture is at 45 degrees to surface, that is at 45 degrees to the tensile strength, and the net effect is like that. So you can have if you can have a flat specimen, when it fractures it can be like this, or it can go like that, and if it's thick one, then it can go like that, again it comes down there. But again, this is more or less a ductile failure. Thin section left, shear only, and thicker section in this. So there is a minimum thickness. There is a minimum thickness above which the material becomes more brittle. So in this case, so if you use very thick specimens, even if it's steel or otherwise, if you use very thick specimens, it can become partly brittle. Okay, so this part is ductile, but if it's very thick, then you have some part ductile and some part is brittle. So please remember that. If you have a very thick specimen doing tensile testing, so there is a minimum amount of thickness which you have to maintain if you want to get thin section, and thicker section. If you have thicker section, so this becomes cup and cone, so this part becomes brittle. But in general, for whatever you do, even if you have very thin specimen, there is only very small fraction. Maybe if you 2%, 3%, 4% will be, you will have a brittle fracture thing. But that's not much more important. But you have to know what is the, so when you do the fracture toughness, K1C, would you remember K1C? There has to be a minimum thickness above which you have to do the testing. Yes, sir. Fracture toughness, okay? K1C, you're doing it like that, you have to have a minimum thickness. Because if you do that, the stress intensity factor keeps coming down with that thickness. And that the lowest value of the stress intensity factor is the K1C. Okay? Yes. Mechanism, ductile fractures offers by formation of microvoids and their subsequent coalescence. And that's how the crack grows. As we have seen before, so you're applying sigma max, there are voids, and voids are growing, and the crack is going through the voids, through the grains, and eventually this is the lower surface, this is the upper surface. So this is subsequent crack growth, ductile stress. But if you are looking at microvoid happens decohesion or cracking of second phase particles. So all these things can happen, but this gives you considerable plastic flow, localized. And plastic flow means it takes up energy and requires the expenditure of a large amount of energy. So if you are in a bridge, and going back to the question which you had, if you are in a bridge or if you are driving a truck in a bridge and the bridge has some crack and the truck is keep putting a lot of force downstairs, and then the crack can proceed easily, then the bridge will collapse. But if you have other things like steel rods or composites which will absorb those energy and which will create minor cracks and things like that, so the bridge will eventually crack, but maybe after 20, 30, 40 years. So you have enough time to modify the bridge. Okay? So that is what, and because I have traveled many times in America, many times I could see that some bridges are stopped. They are not used for traffic. Why? Because they are checking and they are modifying the bridge. They are actually repairing the bridge, things like that. But if you have this carbon fiber reinforced plastics together with steel tubes, concrete has steel tubes anyway, so those things actually take a heavy volume you are putting inside. So it is going all through like that, okay? And if you can put some carbon nanotube in the epoxy matrix, then also to crack the epoxy it will take much more. So create void, so anything. And also we had done some work 2-3 years ago where we actually put not carbon nanotube, but we put short milled carbon fiber. What is short milled carbon fiber? It's against the waste material and it's very cheap. And then we put it in the epoxy, and what we could find that gave enormous strength in the epoxy, and we put that modified epoxy and we made composites with that. But I did again work with mechanical engineering department, and then in 2016 when US Innovations in Austin, Texas had their event, so they invited for new projects, and I sent them that paper which was published in Journal of Building and Construction. So they invited me to go there and make a presentation. They gave me a 3-hour table and things like that. And it was fortunate that before I went there, I may have mentioned it, I sent the paper to Professor A.S. Argan in MIT. I said, sir, please have a look. He said, yes, I'll give you go ahead. It will be good. So I wanted to check because, and then, so it was like that. If you want to put fly ash in this epoxy, and you can make it tougher. So it's a very cheap material, and you use that epoxy to make the composites. It's short milled carbon fiber. Mill. It's a long carbon fiber, just cut it into short things. Short milled. Do you want me to write it down? Milled is cut down. I want to clean up the other thing. Where is the duster? Right? Oh, do I have it in front of me? Why do I take the duster that way? Thank you. Thank you very much. I missed your name. Humaira. Thank you, Miss Humaira. Short milled carbon fiber. This is C. And this is a very cheap material. You can get it from companies, so you don't have to do anything, okay? They are standard things, so you can put 5, 10, 20. And what that will do, that will, in the epoxy, that will give you extra surfaces. That will make the epoxy matrix much tougher. So that will generate much more toughness. All right? And when I was doing that work, I did it with Professor Dr. Raman Singh. He's a PhD. It's not the Raman Singh who is the Chief Minister of Chhattisgarh, no. We have my friend Dr. Raman Singh at Monash University. He then his colleague Dr. Excel, and also a professor from North Carolina State University, and he is a civil engineer. So we had mechanical engineering, chemical engineering, materials engineering, and civil engineering together. We did this work. All right? Sorry? It is what short milled carbon fiber. They take it from any composites industry which have carbon fibers, and the waste material, a lot of carbon fibers, fabric is considered as a waste material and thrown away. So they say, don't throw it away. They cut it into small pieces, and they shed. It's like a modified carbon fiber. Carbon fiber is much expensive, and then it's like another waste material, short milled carbon fiber. So, but we again, when we put there, it shows that it's not an ordinary material. It can actually low cost, but it can be very toughened material. And it was published in, this paper was published in Journal of Building and Construction Materials. And the first author was my former PhD student, S.T. Cholake. He's from Pune. Cholake, then you can put my name. So you can find it out if you go to the website. S.T. Cholake. This is Journal of Building and Construction Materials. It's about 2-3 years ago published this paper. But I was quite happy when US Innovations, and they are very particular. United States Innovations, they have Army, Navy, Air Force all together. Anything they do it thorough investigation. Speak up loudly. Hmm? That is what all these things will prevent. That's what I'm going to say that. So if there is a crack developed, if you make it tougher, it will not fail immediately. It may bend. It may bend and it can show that it has deformed. So stop the things. So bending is a plastic deformation. But if it fails immediately, that's a brittle deformation. So I think you can do anywhere. Bridges, whatever is, if it's taking load. Now sometimes suspension bridges and their structure is different. So the civil engineers develop all these new structures, okay? But in any case, when it comes to failure, brittle failure and plastic failure, brittle failure does not care about time. And plastic failure is that there is a defect, crack starts, and plastic failure said will hold you for some time. So the cars can come out and sometimes, even if the bridge fails, it may take a few days to fail, so people can move out. So those kinds of toughening things can be given by these systems. And as I said, you have to think about it before construction of the bridge or during the maintenance of the bridge. Don't do it, अगर देखेंगे अगर कुछ गलती हो तो करेंगे, no ऐसे नहीं. पहले से करना है, गलती हो तो वो थोड़ा चक्कर लगाएगा, तब हम रुकेंगे. But if it gives instantaneous failure, it's very bad. Okay, microvoid formation can serve like decohesion and cracking of second phase particles. And the process of microvoid formation and coalescence involve considerable localized plastic flow. But again, if it's localized plastic flow means it still needs expenditure of a large amount of energy. Hence, materials which fail in a ductile matter have good toughness. And ductile matter means it gives you time. It deforms, you can see that. All right? So whatever construction materials you are using, please make sure it has enough plastic crack propagation mechanisms absorbing energy. Void nucleation growth. Okay, I'll try to finish it in about 10-15 minutes. Okay, today. All right. Particle fracture occurs when the failure strain of particles is exceeded. Decohesion occurs due to dislocation pile-ups. So these are the mechanisms which show you have a particle and it cracks or it goes through that. So this is edge, this is screw, cracking, this is screw, and eventually there is a stress setup. Generation of a loop around a particle, note that the edge and screw components are opposite sign. So the edge can make it crack easily and screw will not make it crack easily. And that moves dislocations which generate loops around particles. But this is applied for metal materials. And then this can go up through piled up pools and eventually the cavity form void. So these are the mechanisms which actually lead to the particle matrix interface, spend the energy, and the void is created. And then, if the void grows, it will take more energy. Many pile-ups occurs of different slip planes if you have a metal system, and the voids grow by assimilation of dislocation from these pile-ups. So it takes time. So here it is actual situation, and here is void growth. So this is how there are two types of dimple initiation. Here, you have two different magnification. This is about 7 micron, and this is about 3 micron. This is about close to 1/3 of this. So area-wise, this is about 9 times of that. So what you are seeing here, you are seeing here also, but at a much higher magnification, about 9 to 10 times. So now you can see what you are seeing there, how this thing said void is forming there. Numerous small particles include nuclear, have small microvoids and few larger particles. Again here, the scale bar is 5 micron, and here the scale bar is 2 microns. That means it's 2.5 times more. Okay, magnification. So 2.5 times 2.5 is how much? 2.5 times means 2.5 times means 5. Okay, and about another 5 to 6% higher magnification. So this is a lower magnification. This is about area-wise about 5 to 6 times high magnification. So this shows how the things happen. The large microvoids. But as soon as it forms microvoids, it takes up energy. This is going to be one of the last few slides which I'll be using today. If you have a crack, or this is a notch, you know, notch samples. If you have a notch, there are a defect, and when the load is going up, that means your load is going up and down. So this displacement is more. Some of this particle crack, and eventually from this notch tip, typical notch tip radius is about 0.25 if you're using a notch specimen. But if you're using a normal specimen, then the notch tip, the crack tip or the tip of the area, maybe 20 microns or 30 microns. But as soon as the crack starts, this generates sharp stress about 3 to 4 times or more, and then they start breaking. It goes on, keep on going like that. So the rest of the material matrix does not get damaged, but it goes something like that, and eventually it comes up to here. So you have one piece of material that becomes separated into 2 pieces of materials. So transgranular microvoid. So this is how the microvoids grow. So the same pictures is shown in different magnification. This one is area-wise 4 times more, and this is area-wise, this is 20 times, 5 times more compared to that. Linearly, it is 5 times more compared to that. So that is how you can see this. This is the cracks or voids formation and the crack propagation through them. Figure said 100 magnification, high magnification 100 times. Now if you're saying 100 times is the linear, that means the area-wise it becomes about 10,000 times. The fracture is usually transgranular, and this is how it shows the equiax dimples on fracture surface. So dimples means voids go down, have some depth, and this is the elongated dimples in fracture surface. The fracture keeps on continuing, and the flat surface are more used to shear fracture. So here you can see this is what shear fracture is. This part is shear. What is shear? So this goes that way and that goes this way. So this is the kind of thing. Shear fracture is still a ductile fracture. And then if you have tensile tearing, so now when you are pulling from one end, this is tensile tearing. It goes up here, and this is fracture toughness. You are crack propagating that direction rather than the central direction. So that's a different mechanism. So there are tests for that. And tear failure results from mode 1 loading. So we are coming to mode 1, mode 2, mode 3. Mode 1 is tensile loading at the end of that. Mode 2 is shear type 1. And mode 3 is anti-shear. So these are the kinds of loadings which you can have. All tests should be done in these results, okay? Where there is shear deformation mechanism involved in a loading, please use this and that anti-shear. This is shear and this is anti-shear. So mode 1 is tensile, mode 2 is shear, or mode 3 anti-shear. So that's where I'd like to stop to give you an idea about how fracture mechanics, how fractures can happen in different ways. So whatever way it happens, it happens. So whatever way you can, you make sure you don't let it happen. Don't say, sorry, it happened. You have to work beforehand, and you have to know how things can go wrong. And then, so when you eat some food, before you eat the food, you have to know what are there in the food, whether you are susceptible to that, whether it creates crack in your stomach. After you have eaten the food, then you will have a fair bit of suffering, all right, for some time. So you have to know like that. So these are the kinds of things. So with that, I'll close my... What is the journal? No, that is one. That is another different one. But you go to International Journal of Building and Construction Materials. That is also another publication, the same project, okay? But that is making this matrix. But then if you go to this one, Journal of Building and Construction, put the same Sagar Cholak's name there, and go to the Journal of Building and Construction, that will give you the fracture toughness of those composites, which will be useful for your query.
Journal of Building and Construction.
Yes. Construction Materials. Journal of Building and Construction, JBCM. Okay, we had a... What is it?
Length the milled short fiber.
A few microns. It is. If you can find out the journal, would you pass it on the link to him? Okay. All right. Any more? Huh? You have to sing the Oriya. Okay. Yes. Now my time is over, so you take it over. Thank you. I'll sit here. All right.